Hydraulics is the science of controlling fluid motion to transmit energy, and it plays a critical role in industries ranging from water distribution to deep drilling operations. At its foundation, hydraulics is built on a few key principles: pressure, flow rate, density, and viscosity. At its foundation, hydraulics is built on a few key principles: pressure, flow rate, density, and viscosity. Pressure represents force applied over an area, and when applied to a confined fluid, it is transmitted equally in all directions. Flow rate describes how much fluid moves through a system over time. Together, pressure and flow determine how much hydraulic power is available to perform useful work, whether that work is lifting heavy loads or cleaning a borehole thousands of meters underground. To truly understand hydraulics, we must first understand flow regimes. Fluids don't always move the same way. In laminar flow, fluid particles move in smooth, orderly layers with minimal mixing. This typically occurs at low velocities or in highly viscous fluids. In turbulent flow, motion becomes chaotic, filled with fluctuations, usually at higher velocities. The transition between these two regimes is predicted using the Reynolds number, which compares inertial forces to viscous forces. Laminar flow offers predictability and lower frictional losses, while turbulent flow enhances mixing and improves cleaning efficiency. Choosing and controlling the correct flow regime is a key part of hydraulic design. As fluid moves through pipes and allular spaces, they experience pressure losses. These losses are unavoidable and result from friction between the fluid and the pipe wall, as well as disturbances caused by fittings, pins, expansions, and contractions. Major losses occur along straight sections of pipe due to wall friction, while minor losses occur at geometric changes in the system. One of the most widely used tools to estimate frictional losses is the Dorsey equation, which relates pressure drop to pipe length, diameter, velocity, density, and the friction factor. Managing pressure losses is critical because excessive losses reduce system efficiency, increase pump requirements, and raise operational costs. The behavior of hydraulic system depends heavily on the type of fluid being used. Fluids are broadly classified as Newtonian or non-Newtonian. Newtonian fluids, such as water or light oils, maintain a constant viscosity regardless of shear rate. The relationship between shear stress and shear rate is linear and predictable. However, many industrial and drilling fluids are non-Newtonian, meaning their viscosity changes with shear rate. This makes their behavior more complex and requires specialized rheological models to accurately predict pressure losses and flow performance. One of the most common rheological descriptions used in drilling hydraulics is the Bingham plastic model. This model assumes the fluid behaves like a rigid body until a certain yield stress is exceeded. Once that threshold is reached, the fluid flows with a linear relationship between shear stress and shear rate. This is particularly useful for drilling muds, which must be able to suspend cuttings when circulation stops. The presence of yield stress prevents solids from setting under static conditions. Another important model is the power law model. Unlike the Bingham model, it doesn't assume a yield stress. Instead, it describes a nonlinear relationship between shear stress and shear rate. The key parameter here is the flow behavior index. If the index is less than 1, the fluid is shear thinning, meaning its viscosity decreases as shear rate increases. This is advantageous in drilling because the fluid becomes easier to pump at higher shear rates while remaining viscous enough at low shear rates to suspend cuttings. The Herschel-Bulkley model combines the strengths of both the Bingham plastic and power law models. It includes a yield stress component as well as a nonlinear shear-dependent term. This makes it one of the most accurate models for describing complex drilling fluids. By accounting for both yield stress and shear thinning behavior, it provides better predictions of pressure losses and hole cleaning performance, especially in challenging well geometries. In practical hydraulics, these rheological models are integrated into engineering equations to calculate annular pressure losses, pump pressures, hydraulic horsepower, and equivalent circulating density. These calculations ensure that sufficient energy reaches the drill bit while maintaining wellbore stability. Hydraulic horsepower at the bit is especially important because it directly influences rock breaking efficiency and rate of penetration. Proper distribution of pressure and flow through the bit nozzles determines how effectively formation is removed. Optimization of bit hydraulics focuses on maximizing energy impact at the bottom of the hole. This involves selecting the right nozzle sizes, balancing flow rate and pressure drop, and ensuring efficient jet velocity. The objective is to enhance bottom hole cleaning, prevent bit bowling, and improve drilling efficiency without exceeding pump or formation pressure limits. Even small adjustments in flow rate or nozzle configuration can significantly affect overall drilling performance. Closely related to bit hydraulics is mud carrying capacity. Once cuttings are generated, they must be transported efficiently to the surface. Carrying capacity depends on annular velocity, fluid density, viscosity, yield stress, and well inclination. Adequate annular velocity ensures that the cuttings remain suspended and do not settle. In vertical wells, turbulent flow may enhance planing, while in highly deviated or horizontal wells, sufficient yield stress and proper rheology becomes more critical. Poor carrying capacity can lead to cuttings accumulation, stuck pipe, and costly non-productive time. In conclusion, hydraulics is a dynamic interplay of pressure, flow behavior, fluid properties, and energy management. From understanding flow regimes and pressure losses to applying rheological models like the Bingham Plastic, Power Law, and Herschel-Bulkley, each concept contributes to protecting and controlling fluid performance. When these principles are applied effectively, engineers can optimize bit hydraulics, maximize mud carrying capacity, and design systems that are efficient, safe, and economically sound. Hydraulics is not just about moving fluid, it is about mastering the physics that turns fluid motion into controlled and productive power. If you found this video insightful, give it a like, subscribe to our channel, and hit that bell icon so you never miss one of our videos. Until next time, stay curious and stay informed.